Hello everyone, we're going to talk about section 7.2, applications of Venn diagrams. So in section 7.1 we talked about sets and all the basics of it and everything. And we also talked about one of the main ways to depict sets or see them in like a visual way is to use Venn diagrams. So we use them in our last section to mostly describe the intersection and union of sets or disjoint sets and subsets. So these are often viewed as circles representing the sets, and the rectangular section around the circles represent the universal set. So you've always seen it drawn inside of like a rectangular or maybe square shape, and then you'll usually see a little U in the bottom corner somewhere, and that just represents the universal set or all the values that we're thinking of, and then the circles will represent different sets, and then the overlappings will be where those sets overlap. So in figure 5 here that we're looking at, we see that in the first picture A, where it says 2 sets lead to 4 regions, numbering is arbitrary. We see that we have 2 sets, A and B. They're each colored by what they are, so A is blue and B is that pink color, and then 3 is purple because that's the numbers that they share in essence. And also the elements not included in either, so that will be in the white rectangle of our universal set. Those will be all the numbers that aren't contained in sets A or B. Then in figure B, which says 2 sets lead to 3 regions, so we see there's only 3 regions in this case because we have the universal set, or all the space in between the 2 circles. And then we have A, which is 2, and then B, which is 3. And we see that they don't overlap at all, so there's only 3 regions that we're even considering. Then we see C, which is 2 sets lead to 3 regions. So once again, we still have 2 sets, but it's still 3 regions because we see our universal set as the white background. And then we have our set B, which is 2, or the blue ring, and then we have A, which is 3. So this Venn diagram, this C in figure 5, so figure 5C, we see that this represents the subset because we see that A is inside of the set B. So that's what a subset would look like according to Venn diagrams. So let's get into our first example. So we want to draw a Venn diagram similar to figure 5A. So in this case, we're thinking about figure 5A here. So we have where these 2 sets are overlapping. So we want to draw Venn diagrams similar to those, and then we want to shade the regions representing each set. So we have A intersect B complement, or B prime. First, let's just say what each set is in terms of the numbers. So if we want to say A is equal to, and then our set, what we're paying attention to are the numbers. So here we have A, so this is our A set here, and we see inside of our set we have the numbers 2 and 3. So we can say A is equal to the set of 2 and 3. Now let's just find B. So we do the same thing. We see this is B, here's our circle, and we have 3 and 4. So since we only have the numbers 1, 2, 3, and 4, this means our universal set is just 1, 2, 3, and 4. Those are all the numbers in our whole image here, in our whole Venn diagram. All right, so we found what our set A is, what our set B is, and what our universal set is. So we're trying to find A intersects with B complement, or B prime. So if we know that B is 3 and 4, and we know that B complement, or B prime, is everything that's not in B, then we can find out what B complement is. So first things first, we want to find out what B complement is. Since we know that B contains 3 and 4, we know the universal set is 1, 2, 3, and 4, then we would say that B complement is just going to be 1 and 2. So let's say B complement is equal to the set of 1 and 2. Sorry, really. So now we have A and we have B complement. And remember, the intersection is the areas that they share, where they are both present. So if B complement is in areas 1 and 2, and A is the set of 2 and 3, well, the only number that they share in this case is going to be 2. So the region that they share is going to be 2. I'm going to move this so we can write our answer there, actually. So move that down there. So this is also like saying, if we're saying A intersect B prime, that's like saying 2 and 3 intersect with 1 and 2. So they both share the value of 2. So we know that this is going to equal just the set of 2. So we need to shade the region. So we see that 2 is going to be this area of A, but not 3, so just this area. So we just shade in this area. Oh, that's so small. Make that bigger. There we go. And that would be it. So with our A intersection of B prime, we kind of broke everything down into what we know exactly what each set is. And then we wrote everything out, and then we just found what they shared, which was the set of 2. So then we just shade in the region of 2, and we're done. And that would be our finished Venn diagram. All right, on to our next part. So now we have A prime union B prime. So in this case, we know what B prime is because we already found it, but now we'll need to find A prime. So let's find A prime. So remember, or A prime, or the complement of A is going to be all values that aren't in A. So we'll say that A prime is going to be the set of 1 and 4. And we know what everything else is. So if we know that, and we say A prime union B prime, and remember that union is any value that's in one or the other or both, so all 3. So we take A prime union B prime, and we know A prime is 1 and 4, and B prime is 1 and 2. So if we're finding the union, it's going to be whatever's in set A, whatever's in set B, and whatever values that they share. And obviously we're not going to write the value that they share twice. So we end up getting, right up here, the set of 1, 2, and 4, because those are the values that are in A and B and both. Because we see 1 is in both, 4 is in A complement, and 2 is in B complement. So now we have the set of 1, 2, and 4. So now we can just color this in. So basically the only value that we're not coloring in is 3, or the shared area. So we can just fill this in. This is included. Just make it clear that 3 would be the only area not. Just fill it in as much as possible there. And there we go. So those would be our 2 completed Venn diagrams. Now we can do a little harder example. So we want to shade the regions representing A complement union of B intersected with C complement. So we see there's just more than 2 sets that we're dealing here with. But it's also important to remember that our original rules, or I guess in our case, PEMDAS, where, parentheses, exponents, all the rest of it, we want to follow the same rules. And we're not really going to see exponents in these cases, but we will see parentheses. So we always have to do what's in the parentheses first. So the first thing we want to do is find B intersection with C prime. But first, let's just figure out what each of these sets are. So we'll find the set of A, B, and C, and U. So looking at our image here, we're looking at our Venn diagram, and we want to solve for A. So let's think of A first. So here's our circle of A all around here. And it looks like the values contained in A are going to be 2, 3, 4, and 5. So we know that A is equal to 2, 3, 4, and 5. Now let's solve for B. So if we think of B here, here's our circle of B. And what we see contained is 3, 4, 7, and 8. So B is equal to 3, 4, 7, and 8. Now I want to solve for C. So if we think about C here, here's our whole circle of C. And we see the values 4, 5, 6, and 7. So we have 4, 5, 6, and 7. Now we know our universal set is just every number in our rectangle. So we see it's going to be 1 through 8. I guess I should start giving it a little tail so you know the difference between a union and the universal set. So we know it's 1 through 8, so we're just going to do ... 8. So we don't have to write out every single number, but we know what it is now. All right, so we found all of the sets. Now we have some complements in our question. So let's just find the complements that we want to find. So we have the complement of A and the complement of C. So let's find just those values, because we don't need to find the complements of every single value, just A and C. So then, A prime is any value not in A. So any value not in this circle. So we see 1, 2, 3, and 4 are inside the circle, so not those. So we just have 1, 2, 3, 4, and 5 all in A. So we have 1, 6, 7, 8. You can also just look at the set that we already stated here. So you can just think of all the values that aren't in this set that are in the values of 1 through 8. Now we want C prime. So we know that C is 4, 5, 6, and 7. So we know it's going to be every value that's not in C. So we see 1, 2, 3, none of these, and 8. So we know C prime is going to be 1, 2, 3, and 8. Okay, so now we found the set of each of these regions. So we're going to do what's in our parentheses first. So do what's in parentheses first. So let's do B intersect C prime. So we know that these values are going to be just the values that they share. So let's write them out. So we know B is going to be 3, 4, 7, and 8. And then we're taking the intersection of C prime. And we already found C prime, which we know is 1, 2, 3, and 8. So now we just need to find the values that they share. So we see 3 is in B, 3 is also in C prime, so we can write 3. 4 is in B, but not in C prime. 7 is in B, but not in C prime. And lastly, we have 8, which is in B and C prime. Now we also see that 1 is in C prime, but not in B. 2 is in C prime, but not in B. And then we see that 3 and 8 are going to be our shared values. All right, so we found that our intersection between B and C prime is the set of 3 and 8. So now what we're going to do when we find the union between A prime and the intersection of B and C prime, we are going to take the union of A prime and the set of 3 and 8. So we know what A prime is. Let's write this out. So we have A prime union, and I'm just going to write the set of 3, 8, because we know that that's what that is now. And we want A prime, and we know that A prime is going to be 1, 6, 7, and 8. And we're taking the union of the set 3 and 8. And remember, the union is all the values in one set or the other or both. So we see here that 1 is in A prime, but not in our set of 3 and 8. 6 is not in our set of 3 and 8, but in A prime. 7 is in A prime, but not in the set of 3 and 8. But 8 is also in the set of 3 and 8. So we don't have to write 8 twice, but now we have every other value. And we see that 3 is in the set of 3, 8, and not in the set of A prime. So what we do is to combine these, and we get to write 1, 3, 6, 7, and 8. So this is going to be our final answer, because now we know that this is our set if we take A prime and the union of B intersection 3 C prime. So when doing problems like these, it's always important that you do whatever is in the parentheses first, and then you just take that answer and finish the problem. So now we get to shade in this region. So since there's a few regions in this case, in our last case there was only 1, 2, maybe 3 regions. So there's more regions in this case, so let's just make a mark of each one and then we'll shade them in. So we see region 1, region 3, region 6, region 7, and region 8. So now we just get to shade it in. So not in region 2, so we can't shade in region 2, but we can shade in region 1. We also have region 6 and 7. And you can shade them all in separately too. So let's do that actually. So let's just start with region 1. So we just shaded all of region 1, ignoring anything else. So fun. Okay. That's our biggest region. So now we don't really have to worry about it. Then we have region 3. So let's shade in region 3. And region 6. Region 7. And finally, region 8. And we see here that the only regions not shaded in are going to be 2, 4, and 5. All right. I suggest when shading in regions to use the method that we just did. So you want to shade in each region separately, and then you see which regions are left over. I don't suggest just like shading in all the regions at once like I started doing. I suggest that you go through and you do it one by one in this case. All right. So now, since we know a little bit more about Venn diagrams now, we can talk about their applications. So Venn diagrams can be used to analyze many applications as illustrated in the following examples. So now, instead of just working with numbers and our sets and our letters, now we're going to be thinking about actual real-life applications of Venn diagrams. So example 3, we have a researcher is collecting data on 200 people. They found that 83 people have CD players, 97 people have iPods, 34 have both, so they have an iPod and a CD player. And the researcher wants to know how many people don't have a CD player, how many people don't have a CD player or an iPod, and how many have just an iPod. So we have all of our Venn diagrams here, and we've labeled them. So we have iPod, CD, both. So let's label, just to make it easy on ourselves. We'll say that iPods are going to be the set I, CD players are going to be the set C, and B is going to be the set of both. Okay, so let's starting with A. And we have all our Venn diagrams drawn out here. So all we need to do is just figure out what sets, and then we're going to shade them in. So I want to know how many people don't have a CD player. So if we're thinking about the people that don't have CD players, we're thinking about all the people that have an iPod or nothing, but not both, because that would mean that they had a CD player. So we're thinking about iPod or nothing. So thinking about our region, we're going to pick people that have an iPod and people that have nothing. So we see here that shading in our region can help us think about these values. So now, but we want to find the actual number. We're not just shading in the regions. So when we assign values to our Venn diagrams, a really good method of doing this is starting in the center and working your way out. So, and by working in the center, we mean whatever thing is in the center. So in this case, our center region would be both, because that's the thing in the middle. It includes everything. So if we know that 34 have both, we start with the number 34. So we can zoom in here, and we say, oh, that's 34. I'm going to make this a little smaller. Now, we know that 83 people have CD players and 97 people have iPods. So it's really easy for us to just go in and just label the leftover regions 83 and 97. I'm not going to write it because it would erase the shading. But it's really tempting to just write that, but we can't, because 34 of the 83 that have CD players also have an iPod. And same thing goes for people that have iPods. 34 of the 97 also have CD players. So just because we know that 83 people have CD players, we can't just fill that in for the spot of only CD players. And we know in all, we had 200 people that we asked. So what we do to solve for this region of our CD players here is we want to take 83 minus 34. And that is going to give us 49. I'm gonna erase that because that's really big. 34. So now we know that 49 people only have a CD player. So now we can do the same thing for iPods. So we know 97 people have iPods. 34 of them also have CD players. So we take 97 minus 34, and that's going to give us 63. So now we know 63 people only have iPods, 49 people only have CDs, and 34 have both. So now to find our universal set, which we know was 200, or to find what's left over of people that don't have any, we would add up all of our values. So we would add 63, 34, and 49. And this gives us a value of 146. So we know people that don't have anything is 56. I can do this here. Because we want 200 minus, and it was 146. This gives us 54. So 54 people don't have an iPod or a CD or both. All right, so we've labeled all of these. Now that we know these values, we can label every single one of our Venn diagrams like this because we know the actual values. The values aren't going to change. But back to our question, we want to know how many people don't have a CD player. So if we're thinking about people that don't have a CD player, we're thinking about the people that aren't included in our set of having a CD. So just a CD or in both cannot be counted. We're only counting iPods, people that only have iPods, and people that don't have anything. And we know these values, we see our area is shaded in, so what we're going to do is we're going to add these together. So we have people that only have iPods are 63, and people that don't have anything is 54. Now we can just add these together, and we get 117. So we say 117 people don't have a CD player. All right, so that is how we kind of use our real life applications in Venn diagrams. All right. So since we know the value of each one of these regions, we're just going to fill in the rest of our Venn diagrams, and it's going to make this go a lot faster. So we know 63 people have iPods, 34 people have both, 49 people have CDs, and 54 people have none. All right, so for part B, we're asking, how many people don't have a CD player or an iPod? So this is going to be no one in this region and no one in this region. So what we have is the region around. Since we calculated the values of each one of these regions, we pretty clearly know the answer. since we already found there are 54 that don't have either, and our question was how many people don't have a CD player or an iPod, we know the answer is going to be 54. So we say 54 people don't have a CD player or an iPod. So it becomes pretty clear once we've deciphered each one of these values of each of the regions that finding our answers to a lot of these questions are fairly simple once you've found values though. So for part C, let's label these again so we know it's 63, 34, 63 people have iPods, 34 have both, 49 have CD players, and 54 have neither. And our last question here is how many people have just an iPod? So if we're thinking about people that just have an iPod, we're thinking about the people in this region. And since we already know the value of this region, we know the answer. We can say 63 people just have an iPod. And there you go. So we actually didn't even need to label our sets here like we did earlier. But this is just another way that we can use our Venn diagrams for our real life applications. All right. So example 4 here. Somewhere along in our chapters, they kind of changed. So instead of seeing things as checkpoints, they're now called your turns. So example 4 is your turn, number 3, for the third one. And we're asking, 100 students were asked which fast food restaurants they had visited in the last month. The results are as follows. 47 teenagers, I think it is, students, went to McDonald's. 46 students went to Taco Bell. 44 went to Wendy's. 17 of them went to McDonald's and Taco Bell. 19 of them went to Taco Bell and Wendy's. 22 went to Wendy's and McDonald's, and 13 went to all 3. So we want to determine how many people only ate at Taco Bell. So we're going to shade in our region. First, we're going to find all of our values. We're going to shade in our region, and then we're going to find how many people went to Taco Bell. So, let's shade in our region first. We'll rearrange that order. Shade in the region first, and then we'll assign the values. So we only want how many people only ate at Taco Bell. So we see here I labeled M. So let's see, M is McDonald's, T is Taco Bell, and W, W went to Wendy's. So we see here we have our circle of M, our circle of T, and our circle of W, and our universal set, which we know we asked 100 students. So, and we want to determine how many only ate at Taco Bell. So we can fill in our, we can fill in our region. So this is the only region we're worried about because we only want how many people only ate at Taco Bell and nowhere else. So we have all of these. And remember, an easy way to fill out our Venn diagrams is you start in the center and work your way out. Because if we added up all of these values that we see right here, if we added up 47, 46, 44, 17, 19, 22, 13, if we added all of those values, that is most definitely not going to equal 100. That is a lot more than 100. And that's because certain values of these eat at all 3, certain eat at 2, and some only eat at 1, and some don't eat at any. So we have to remember, fill in the values. So we start in our center. So we start in the very center here. And this is going to be both. Because we see that all 3, not both, all 3. Because we see that all 3 of these circles overlap, and this is the area where they all overlap. So this is our area of all 3. And we know that this value is 13. So your center value always gets the value that it's given. Whatever value it's assigned, that's the value that it is. No subtracting, no adding, nothing. Then we want to see McDonald's and Taco Bell. We have McDonald's and Wendy's, and then we have Taco Bell and Wendy's. All right, so now we can move on into labeling all of our regions or assigning values. So let's start with McDonald's and Taco Bell. So we have that 17 people ate at McDonald's and Taco Bell, but 13 of those people ate at all 3. So we have 17 minus 13, and that's going to equal 4. And let's box in all of our definitive final answers. So we have 4 people ate at McDonald's and Taco Bell. Then we want to move into our next value. So let's do Taco Bell and Wendy's. So we had that 19 people ate at Taco Bell and Wendy's. But we know that 13 people ate at all 3. So we're going to take 19 minus 13, and that's going to equal 6. So we have 6 people ate at Taco Bell and Wendy's. For the sake of our problem, since we only want to know who ate at Taco Bell, we have all the values that we need. So what we're going to do to determine who ate at Taco Bell, we know 46 people had eaten Taco Bell. Now, out of 46, 13 of them ate at all 3, 4 of them also ate at McDonald's, and 6 of them also ate at Wendy's. So what we're going to do is we're going to take 46, all of our people that ate Taco Bell, and we're going to subtract each of these values. So we subtract 13, we subtract 4, and we subtract 6. So now that we have found all of these values, we just calculate t. So if you subtract all of these numbers, we end up getting 23. So then we can say 23 students only ate at Taco Bell. Since we were only asking, and we can label this 23 now, box it in. Since we were only asking to determine how many people only ate at Taco Bell, we only needed to really find the regions that Taco Bell reached. So we really only needed to find these values here so we could determine this value, because we know that this entire circle was 46. So we just need to find the missing parts to calculate our value. Now, since practice is always important, we found the answer to our question, we have determined our answer. Now let's just calculate the rest of the values. So, we do the same thing as before. So let's start with McDonald's. So we know 47 people ate at McDonald's. We already have 2 of the regions filled out. Now we just need our last region. So we have who ate at McDonald's and Wendy's. we had 22 people, but 13 of them ate also at Taco Bell. So we subtract our 13, and we get that 9 people ate at McDonald's and Wendy's. Now all we have to do is subtract 4, 13, and 9 from 47. So we're going to say 47 minus, and then let's add all these values up. You can subtract each one individually if you would like. Doesn't really matter the way that you add or subtract these. But we see here that we can take 47 minus, let's do 13 plus 9 plus 4. This ends up giving us 47 47 minus 26, and we're left with 21. So 21 people ate at McDonald's. Now we can find the value of the people that only ate at Wendy's. So we filled in already previously every other circle that also contains Wendy's, so we can just find that number. We know 44 people ate at Wendy's, so we can take 44 minus 13 plus 9 plus 6, and there's not a whole lot of room here, so we're just going to calculate this value. We end up getting 16. So we had 16 people only ate at Wendy's. Now, since we have all of our final values, we want to add all of them up and make sure that they either equal 100 or less than 100, because we know that we only interviewed 100 students. So we know that if we add all these values up, it can't be more than 100 or else we have done something wrong. So we add up, and let's just go in a circle here. So starting with McDonald's, we take 21 plus 4 plus 23 plus 6 plus 16 plus 9 plus 13. So we have, these are all the values that we've already calculated. And when you add all these values up, we're going to get 92. So we had that 92 of the 100 students ate at some fast food restaurant, or a number of them. So this means that there were 8 students who didn't eat at a fast food restaurant. Well, that was labeled. So they didn't eat at McDonald's, Taco Bell, or Wendy's. So that is how we would find all the values of a Venn diagram, especially one that's a little more complex here with 3 circles instead of just 2. All right. So we'll load that up a moment. A word of caution. Common error in solving problems of this type is to make a circle representing a set and another circle to represent its complement. Once you draw a circle for a set, anything not in the circle is not in the set. So a common error that a lot of people make is they'll have, they'll have a universal set, and let's say they have A and B, and then we have our universal set. And something that a lot of people will do when they think, oh, okay, well, what's a complement? They'll draw some other circle, and they'll say, okay, well, this is A complement. Or maybe they'll draw another circle over here and say, oh, this is B complement, or something like that. And you cannot do that. A complement is just any value that's not already in the set. So it's just anything that's not in the set. And you can add those if you know the values of them. Or, oh, yeah, I'll redraw that. You can add values or not that. Or anything along those lines. You can find the values that are in each case, or maybe the set of numbers that are in each set, and you find what values aren't in the set that you're thinking about, the set that you're taking the complement of. You cannot draw another circle saying, oh, this is the complement. Because if you draw another circle, either it's going to overlap the complement that you're, or the set that you're taking the complement of, and then it's not the complement because it will include other values, or you draw it outside the circle, and if you do that, then you're excluding the other values that wouldn't be found in that circle. So no drawing a circle, the complement is just everything that's not included. So in the examples we just went over above, we started with the information specifying the relationships between all categories. And we already said before, this is the best way in solving problems like this with Venn diagrams. You start by specifying the relationship between all of them, or the center value, and you work around it, you work outwards. In the previous section, so in section 7.1, we used n of A, remember that value, to indicate the number of elements in the set of A. So if A were the values of 1 through 10, then n of A would be 10 because there are 10 elements. So we can also use it for this rule that we're going to be using. We have the union rule for sets. So this is saying that n, or the number of elements, in A union B is equal to n, the number of elements in A, plus n, B, the number of elements in B, minus n, the elements of A intersect B. So that's with both of them. And we know that this makes sense because A union B is all the values in A and B and both. So if we take all of that number of elements, and we know that our number of elements in A and our number of elements in B, some of those elements are going to be shared, and that would be the intersection. So it would be the shared elements. And when we write out our unions, or our sets that come from taking the unions of other sets, we don't rewrite values that are in both. So this union rule makes sense because you're taking the number of elements in the union of A and B, and you're taking the elements in A and the elements in B, and you're subtracting the ones that they share. So essentially, by subtracting the ones that they share, you're subtracting the duplicates. So now we're going to put this in practice. That's just how it makes sense, but now we're going to actually use this. So example 5, which is another your turn, we have a group of students are sitting in a lounge. All are texting or listening to music, or both. 11 are listening to music, 15 are texting, and 8 are doing both. How many students are in the lounge? So what we're trying to find here is how many students are sitting in the lounge altogether. This is going to be our universal set. We're trying to find the universal set. So we know that the universal set is going to be all of the values, or all of the students sitting in the lounge. So if we just want to take all the students that are in the lounge at all, we're essentially taking the entire box. So as always, we want to start in the center. We're saying 8 are doing both. And we say that 11 are listening to music, but we know 8 of them are doing both. So we say 11 minus 8. That's going to give us 3. So 3 are just doing, are just listening to music, sorry. So we have 3 are just listening to music. 8 is listening to music and texting. So now let's find the value of people that are texting. So we have 15 people are texting, 8 are doing both. So we subtract 8, and we end up getting 7. So in this case, we don't have anyone not doing anything. So we have 0 people not doing one of these 2 activities. And this is because we know in our question we say all are texting or listening to music or both. So we write our Venn diagram the exact same way, and we just indicate that there are 0 people not doing one of the 2 activities, because we know that all of them are doing something or both. So now we have all of our values. And remember our rule. So our union rule is going to be N of A with the union of B is equal to N of A plus N of B minus N A intersect with B. So we know these values. Let's let A equal the students listening to music and we let B be the students texting. And we know these values. We know that 11 are listening to music and 15 are texting. And then 8 are doing both. So we know this means that the number students listening to music is 11. The number of students texting is 15. And we know that if they're doing both, that means we're thinking about the intersection. So we get that both is equal to 8, which means that N of A intersection B is equal to 8. So we found all of the students, or the values, or the number of elements in each one of our set. So now we can use our rule. So we know N elements of A union with B is equal to N of A plus N of B minus N of A intersect B. So we have N, A, union B is equal to, and now let's plug in our values. So we know N of A is 11, N of B is 15, N of A intersect B is 8. So this gives us 11 plus 15 minus 8, so that's going to be 26 minus 8. And we get that N, A union B is equal to 18. So our final answer, because we want to know how many students are in the lounge, so how many people are all there, and that means our union, which is what we're solving for. So we can say ugh, there are 18 students in the lounge. Since we drew ourselves a Venn diagram to begin with and solved for all of our values and filled it in, we could have just added up our values through our Venn diagram as well, but we would like to use our union rule. So our union rule would be helpful in cases like this. It's also helpful if you don't have a Venn diagram, or maybe you can't draw a Venn diagram, then our union rule is especially useful because we can't really visualize it. All right, then we have that when A and B are disjoint, then n of A intersection B is equal to 0, because we know that A intersect with B is what elements are in both sets. So if they're disjoint, that means they don't overlap at all and they have no similar element. They have no same element. So then we know that the number of elements in A intersection B is just 0 because they don't share any elements. So then the union simplifies to n A union B is equal to n of A plus n of B, since n of A intersect with B is just 0. And the union rule is only valid when A and B are disjoint. Or better to say, this union rule. And we're talking about this fact right here. So that's only valid when A and B are disjoint. When they're not disjoint, we use the official rule, which is what we got from the book here. So when they are disjoint, that fact is valid. When they're not, we use the official. All right. Now on to our last example. We have example 6 here, which is going to be number 44 in your book. We have that most math professors love to invest their hard-earned money. A recent survey of 150 math professors revealed that 111 invested in stocks, 98 invested in bonds, 100 invested in certificates of deposit, 80 invested in stocks and bonds, 83 invested in bonds and certificates of deposit, 85 invested in stocks and certificates of deposit, but 9 didn't invest of any of the 3. So how many math professors invested in stocks, bonds, and certificates of deposit? All right, so first things first, let's label everything. So we're going to let A be stocks, B is bonds, and C is going to be certificates of deposit. So when we have our Venn diagram here, we have A, which is going to be stocks. So where's my mouse? Here. So A here, this is going to be our set of stocks. B is going to be our set of bonds. And C is going to be our set of certificates of deposit. And they're all within our universal set, which we know there's going to be 150 elements in our universal set. So now since we found everything, well, we want to use our go-to method of filling in Venn diagrams, and we want to start in the center. But our final answer, which we need to find, is how many math professors invested in stocks, bonds, and certificates of deposit. So our final answer that we're trying to find is our center. So we don't know our center. That's the only thing we don't know. But we know all of the other values, but we don't know the center. So what we're going to do is we're just going to put an X, because we don't know. And we can label our other regions here, so we know this is all 3. This is stocks and bonds. This is stocks and certificates of deposit. And this is bonds and certificates of deposit. All right. So our very center, which is going to be all three, is just X. Now we need to label every region that we need to find. And of course, we know that since we're trying to find X, this is the region we're solving for. But in order to find X, we'll need to find every other value first. So, if we start with maybe our easiest value in the list here, we want to think of 9 didn't invest in any of the 3. We know that value. That value is certain because we know that 9 didn't invest in any of them, so we know that 9 is going to be in the region around the sets. 9 does not depend on who invested in all 3. So we can write 9. It's 9 people on the outside. Then we want to fill in the regions directly around our center. So let's start with stocks and bonds. We know 80 people invested in stocks and bonds. So we know this region here of A and B is equal to 80 minus X. And since we don't know what X is, that's what we have to leave it as. We have to leave it as 80 minus X. Now let's go on to who invested in bonds and certificates of deposit. And it looks like there were 83. So this region is going to be 83 minus X. Then we want to see who invested in stocks and certificates of deposit. It's going to be our sets of A and C. So we know it was 85 minus X. All right, so now we've determined those regions. Now we have to determine the regions of who just invested in stocks, who just invested in bonds, and who just invested in certificates of deposits. We know that the number of the people that invested in these different categories singularly is the addition of all of the other regions. So we get, if 111 people invested in stocks, we have to take 111 minus, and this is going to be 80 minus X plus 83 minus X. So we know that that is going to be the value of A. Then we can go on to who invested in bonds. So we had 98 people invested in bonds. That wasn't 83. This is supposed to be 85. Because we take this and that. So for B, who invested in bonds? We had 98 invested in bonds. So we take 98 minus, and we add up all the other regions. Also, I forgot A, so don't do that. All right, after. So we have this, all of this value here. So let's put these in brackets, actually. So we want to add up these 3 regions. So we have 98 minus 80 minus X plus 83 minus X plus the actual value of X. Putting these in brackets now. All right. Then our last region, our certificates of deposits, we had 100 people invested in certificates of deposit. So we have 100 minus, we're drawing these in brackets now, 85 minus X plus 83 minus x plus x. And then we know the people that didn't invest in any is 9. So let's start by finding these values. So we can simplify A, B, and C a little bit farther just by simplifying what's in our brackets. So let's start with A. So we know that A is equal to 111 minus 80 minus x plus 85 minus x plus x. So now let's simplify what's inside of our brackets. We get that A is equal to 111 minus 165 plus x. That's going to give us that A is equal to negative 54 plus x. So that is our new value of A. So instead of having this really long equation inside A, let's simplify it down. So we know this is going to be negative 54 plus x. So let's do the same thing for B. We know that B is going to be equal to 98 minus 80 minus x plus 83 minus x plus x. This is going to give us 98 minus 163 plus x. And this is going to be equal to B is equal to negative 65 plus x. All right. So now since we know our value of B, let's replace this really long equation. So we know that B is negative 65 plus x. And now let's do the same thing for C. We get that C is equal to 100 minus, and we get 85 minus x plus 83 minus x plus x. This is going to give us 100 minus 168 plus x. So we know that C is going to equal negative 68 plus x. So now we can replace this equation as well. All right. So we've simplified down all of our equations here for A, B, and C. Now we can move on to trying to find how many professors invested in all three. So we know that 9 people didn't invest in anything. So let's label the things we know. We know 9 professors didn't invest at all. We know that we interviewed 150 professors. So 150 professors were interviewed. So this means 150 minus 9, which is equal to 141, professors invested and at least 1. Since 9 didn't invest at all, 150 were interviewed. That means 141 professors invested in at least one of these things, whether it be stocks, bonds, or certificates of deposit. So what we can do is we can take the number that we know is the combination of each one of these values in the region, and we have one variable, which is x, for each one of our equations, and we can take the sum of all of our equations and set it equal to 141, because we know that each one of these values is some portion of 141. So let's do that. So we can say 141 is equal to, A is -54 plus x, B is -65 plus x, C is -68 plus x. Now let's move on to our center, or our ones closer to the center. So we can take 80 minus x plus 83 minus x plus 85 minus x. And then we have our center, x. So we have the combination, or the sum, of each of these regions, and we set it equal to 141. So now all we have to do is simplify and solve for x. So if we simplify this down, which I highly encourage that you pause the video and do, you should end up getting a very measly 61 plus x. Once you add all these values up, your constants become a positive 61. And if you look here, we have plus x, so 2x, plus another x, 3x, minus x, 2x, minus x, 1x, minus x, 0x, plus our final x. So we get 141 is equal to 61 plus x. Now all we have to do is solve. So we subtract 61 on both sides, and we get that x is equal to 80. So we know 80 professors invested in all three. Now, if you notice, well, let's see, between A and B, or between our stocks and bonds, 80 people invested. That means that 80 people of the people that invested in just stocks and bonds also invested in certificates of deposit. Let's go ahead and fill in our Venn diagram. So we know 80 people invested in all three. Let's make this a little smaller. And this was our region we were trying to find, so let's shade that in again. $80 minus x, since we have 80, so it's 80 minus 80. We get that nobody invested in just stocks and bonds. Now moving on, we want to see who invested in bonds and certificates, just those two. We have 83 minus 80, so we get that 3 people only invested in bonds and certificates of deposit. Moving on to who invested in stocks and certificate of deposits, we get 85 minus 80. That's going to be just 5. So 5 people only invested in stocks and certificates of deposit. Then Moving on to our larger sets here. Let's see, we have set A, which is negative 54 plus x, which is 80 in this case. So negative 54 plus 80 is going to end up being 26. Then we want to take negative 65 plus 80. It's going to be 15. Then we're going to take negative 68 plus 80. That's just going to give us 12. So completing our Venn diagram, we get that 9 people didn't invest in anything, 26 people only invested in stocks, 15 people only invested in bonds, 12 people only invested in certificates of deposit, 5 people invested in stocks and certificates of deposit, 3 people invested in bonds and certificates of deposit, 0 people only invested in stocks and bonds, but 80 people invested in stocks, bonds, and certificates of deposit. If you think about it, our question kind of gave us a little hint. We said that most math professors love to invest their hard-earned money. So if they're going to invest in one, you may invest in all 3. But to make sure that we're right, we know that 150 math professors were interviewed. So the way to check and make sure our answer is right is we need to add up all of our values. If we add up all our values and they equal 150, we know that our answer is right. So if we add up everything, we can say add up all our finalized values to make sure they equal 150. So we know we have 80. Here a little bit. So we know we have 80 plus, let's go around our center, plus 0, plus 5, plus 3. Then we have plus 26, plus 15, plus 12. Then we have the 9 that didn't invest in anything. And if you add this up all on your own, you should get that it's equal to 150. That is how we know that our answer of 180 professors invested in all 3 is correct. All right, so that is how we end up using Venn diagrams for real life application, determining which sets are which, and helping us solve our more complicated questions that involve sets. So that concludes our section on 7.2. As always, if you have any questions at all, don't hesitate to email me or talk into my office hours or send me any emails or ask any questions in the online question form or anything along those lines. Here's my cat. She says goodbye. And I will see you all virtually later.